general relativity, step by step. Last time I was working with a generalization of spherical space here, and we've got this nice diagonal metric tensor here, and I evaluated a single Christoffel symbol here. And I made the observation that this was quite a lot of work, and there's quite a lot of Christoffel symbols to evaluate. So what that tells me is that we should be using a computer algebra system to lighten the algebraic workload on us. It's not difficult, it's just time-consuming and intricate and error-prone. So I've got maxima here, just close that, and we've got this nice little user interface here. This is just maxima, or WX maxima, it's a nice front end, and I'm going to show you how to use it to calculate the Christoffel symbols and ultimately the Ricci tensor for this generalization of space. So first of all we need to load C tensor, which is this nice package of tensor calculus that Maxima provides for us. Then we need to specify the coordinates that we have, which are going to be t and r and theta and phi, semicolon. There it is. It's not typeset it particularly nicely, but there it is. Now I need to specify a matrix. LG becomes matrix, and we specify the matrix. The matrix I want to do is this one up here, and I'm going to specify it row by row. Matrix, this is the metric tensor with the indices downstairs. So it's f of r 0, 0, 0 for the first row, 0, 0, 0 for the first row, comma, 0, oh no, it was minus f of r. Minus f of r. That's going to be 0, g of r, 0, 0, comma, 0, 0, r squared, 0, 0, 0, 0, r squared times sine theta. Oops, sine theta squared. It's easy to forget that squared, and if you do, it'll drive you nuts because everything goes wrong. There it is, there's my metric tensor. Minus f of r, g of r squared, sine squared theta. Nice. C metric calculates some stuff behind the scenes, done it says, and now I can type Christoff, and then the option we need is MCS. I'm not entirely up to date with how the latest version works, so MCS just works, so I'm going to use it. And here, in a blink of an eye, it's evaluated all the non-zero Christoffel symbols. Remember there were 32 of them altogether, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. So the majority of them are 0, and that's a reflection of the fact that we've chosen quite a symmetrical set of coordinates for our physics. And indeed, the first one that we evaluated was TTR, which is this one here, which as you can see is f dash over 2g. Oh no, it was this one I evaluated, f dash over 2f, there we go. So there's another Christoffel symbol up here, which is not which is not altogether straightforward, but we've got a whole bunch of non-zero elements here. I can do a little bit more work. I can specify the Ricci tensor, and I think I need to send it true here. True, semicolon, there we go. And these are the elements of the Ricci tensor. You remember that the Ricci tensor is a twice contracted version of the Riemann-Christoffel tensor, and we've got 1, 2, 3, 4 non-zero terms here. Of course, it's symmetric, so we should have 10 terms altogether, the diagonal and the upper diagonal terms. But only 4 of them are non-diagonal. Only 4 of them are non-zero, I'm sorry. Time, RR, theta, and phi. And there they are. And as you can see, they are a complicated mess. Well, there it is. There are the Ricci tensors. So what we need to do, because the Einstein field equations specify that in a vacuum, the Ricci tensor is equal to 0 identically, we need to solve this equals 0, that equals 0, this equals 0, and that equals 0 simultaneously, which I'll do in a minute. Okay, stop there. I'll do that in the next screencast. Stop.